All right. So here we are with the second half of the lecture about herd immunity and stuff. So what I want to do now is two things. One is to carefully brainstorm how do we even do proper modeling in this case. Like, what does it look like? What does proper modeling look like? And second, to actually model it. So I'm actually not sure whether I should do it with herd immunity or whether I should do it with this parameter that we recently introduced, that we just introduced, which is the infectious period. It almost feels more interesting to look at the infectious period. So you know what? Let me actually change the plan right now on the fly. And I will change it in the following ways. Brainstorm proper modeling and what it means for this model. That's one thing. And the second thing is, instead of modeling herd immunity, perform one good proper analysis of two parameters, of any two parameters. And what I mean, yeah, you will see. And actually, you'll see what I mean by proper good analysis. And what I want to do in this case is to do the probability of transmission. In this case, transmission probability, and infection period, and period of infection. Because I think that's the most interesting pair. And of course, I want to have the most interesting pair for myself. With herd immunity, it will be a little bit easier, so I will leave it as an exercise for the audience, for the reader. Okay, but let's start with proper modeling. So let's go down again. Let's look at our model, and let's think about what are the parameters of this model. So we need to think about two things. What parameters does this model have? So we made lots of assumptions. Some of these assumptions are more obvious, some of them are less obvious, but it's nice to run kind of an inventory of all the assumptions that we've made and of all things we could change with this model without changing the model itself. Like, what flexibility is already there? What are the parameters that we can play with? And second, we can look at some of the outcomes, some of the measures that we can take from this model. Like, what can we even measure about it? So let me create a new cell, and it will be a text cell. I will be using it for an inventory of this model. So two things, inputs and outputs. Outputs. So inputs, parameters, and outputs or measures, things to measure. So let's think of inputs first. So let's look at that. What can we change about the model? So here we have a model of a pandemic. What can we change? What parameters do we have? Basically, we're creating a thingy. We're creating a network. That's one thing. And then we run the pandemic. And because we coded it in a reasonably sensible way, many of these parameters are like right here. We see them. Hopefully most of those, like ideally all of those should be here. Actually not quite all of those, because some of them are hidden, but most of those are here. So let's start with the creation. So obviously network type, right? Should I use numbers or let's use numbers. Network type. And right now we use the Barabasi-Albert. We use the Barabasi-Albert model, but we can either compare it, like contrast it with a different model, or we can mess with it, right? We already messed with it once. Last week we eliminated, so we created everything nicely, and then we identified the biggest, the most hubbest of nodes, the nodes with highest degree, and we eliminated it. So that's one type of messing around that we could do. But there may be some other types of messing around. You can remove some nodes, you can remove some connections based on some logic, or even randomly, or you can compare the case when you remove some connections randomly to the case when you remove them with some pattern. Or you can add some nodes, you can create a network and then throw some nodes in. Or you can rewire things. So you can decide that these two nodes will no longer be friends, but instead you will like disconnect this node from this node and connect it to some other node based on some principle, right? We will actually do that this week, next week, next week. I think, yes, next week. Maybe this week. We'll see. So yeah, we can do that. Or for example, like, so this network is not modular, it's not particularly modular. There are cells, there are nodes with lots of connections, there are nodes with few connections, but we don't have groups. It's not like we have, you know, like in the real world, you have people forming certain social groups on for different reasons. Maybe there is a company that employs lots of people. Maybe there are two companies in a city that employ lots of people, and so people who work in the same company are more likely, same factory or something, are more likely to know each other and be friends with each other. Or maybe there are 5 churches in the town, and people who go to the same church, even if they go rarely, so they don't necessarily have this giant node connecting them all, but they are still belonging to a family of Catholics, will be more likely to make them, you know each other compared to another family who are, I don't know, what are the alternatives, like Muslim or Sikhs or something else, Baptist. So, or maybe the city is divided, like many towns around here are divided, and people are kind of, some are right wing, some are left wing, and they're more likely to be friends with each other. I mean, friends within their group than between their groups. So none of these dynamics is here right now. These networks are not modular. So you can try to make it modular. How can you do that? Because I think some of you indicated that you may be interested in that as a potential project. Let me just tell you, like, what can you do? So what does it mean for a network to be modular? Let me throw some ideas around. So, you know, it means that you have a network. That's a network, all right? Artist's rendition of a network. So you have a network of, say, like n nodes and e edges. And then you have another network, also of n nodes and e edges. And you're saying, okay, this network is one and this is another, and they will be modules of my network, right? And so we connect them. But the idea of a modular network is that, so it basically looks, okay, let me draw something. What's that? Oh, that's the change of them. Okay, let me draw. Bing. Nope. Let me draw something like ping, ping. Okay, so I will have like one network and I will have another network. And a network can be called modular when it basically looks like that. When these guys, oh, that's too tiny, too tiny. I don't like that, too tiny. So when these guys are more likely to be connected to each other, so they're connected to each other, see? Very connected, so connected. And these guys are also all connected to each other. But only few of these guys are connected to these guys, right? So like, I may be like, okay, let's keep it like that. Let's keep it like that. So there are connections between the modules, but the density of connections is higher in one group than in another group. So one test about that is like to look at the average connection, average, like you surround. How do people do that? So basically, two nodes within a module are more likely to be connected than a node within a module and a node outside of the module. Right? And if you do the calculation here, I bet it will work. I don't want to write the math here because you can read about that. It's all in the textbook, I'm guessing, somewhere. But is it somewhere around here? Modularity, robustness, spreading phenomena. But you can look for network modularity, and it will give you. See, Wikipedia has a whole page on that. Does it have pictures? Does it have pictures? Not many, but some pictures. But you can look like at more pictures. Oh, look at that! How nice! And that's a good example of a modular network. That's basically what I tried to do. So how to make it? You basically have three options. One option is what I kind of draw here. So you make one network, you make another network, and then you kind of connect them with a few more edges. So like K. So now you have the total network of 2n edges and 2e plus, it's such a pain. Why am I doing that? I should be typing 2e plus k edges, right? And then you can compare it to one network, which is not modular, that has 2n edges, I mean 2n nodes and 2e plus k edges. Right? So if you find a way to right now our network creator is a little bit simplistic in the sense that you cannot actually tell it, please make me a network with a with a small world property with a predictable distribution of degrees, but with a given number of nodes and given number of edges. Right now our network creator takes the number of nodes, but number of edges is kind of coming out of it. I mean, it's like it is whatever it is. We cannot change it. There is no slider to change the number of edges. Only the number of nodes can be changed. So we would have to modify that if we wanted to do this. If we wanted to follow this thing, because in order to compare modular, where is it? In order to compare a modular network to a non-modular network, which is like, I think I should go for an slightly larger. So one larger network, right? We need to be able to create a network with a similar degree distribution, but without modularity. So that's one option. Create a bunch of networks and then connect them. Another option is to go in the opposite direction. So we can take one network and then we can define modules, and then we can try to eliminate some connections, right? So you create a network, say you create a network of these are the nodes, and so you create lots of connections, like these are lots of connections, and then you're suddenly saying, okay, these three will be one module, these three will be another, which means that all connections that are within these modules we will keep, but some of those connections that are between them, a considerable share of those will remove. And so you should go with some probability and like cut this one, but leave this one, but cut this one, but leave this one, So you kind of toss a coin every time. Also doable, but if you like, in order to compare it to something, you also need to keep track of the number of nodes that you have, which won't change, but also the number of edges that will change. And so like a proof of print, just making I guess maybe I should have left this conversation until after we do the model, because the idea is that if you just make one modular network, it doesn't give you don't learn from one point. In order to understand the effects of modularity, you need some control, right? You need to compare it to something. So now suddenly you need to have at least two networks, or better yet, a certain scale of networks from completely not modular to completely modular, but all other parameters should stay as constant as possible. So if you can have the same, you definitely should have the same number of nodes, but ideally you would want to have the same number of edges as well. And ideally you probably want to have the degree distribution also the same. But that gets tricky. It's totally doable, but it gets tricky. And so one option, basically, these are the options. Like the first option was combine. The second option was break. And then the third option is rewire. Where to write that? Like somewhere, rewire. And you can think of that as that's actually the nicest option. I would always go for rewire. So the idea is that you make a modular network, one option. So again, rewire, you can rewire in the modular direction or unmodular direction. So there are actually two subtypes. But you create a network and then you start rewiring nodes. So maybe you define modules and then you separate it, take one connection between the modules and add one connection within the module. That's one option. Or maybe you go the other way around. You somehow create a modular network, and in this case it almost doesn't, it does matter, but you have a little bit of leeway here. And then once you have it, you start rewiring it gradually, eroding this modularity until you have something random. In all of these cases, it matters that the degrees of distribution, you kind of keep track of that. But so if you want to do that, I will post, so let me know, I will post more information about that. But anyway, so coming back to our situation, so network type is important. The second is like the number of nodes, network size, the number of nodes. The third one is the number of edges. And that's it for network creation. So and then there are a few for network for the actual pandemic, but let's park it for a second and talk about network creation. So what's the status of these things? Network type, we have at least 2, maybe 3 types of networks right now. So this Barabasi-Albert, but we also have completely random, or another option, we can mess with the network. So as I just described, we can rewire it, we can play with it. But it is a special, so if you go this way, you probably, this is what I like. I think that's the most interesting part, but it's a little bit tricky. And it's like, it's a hard type of a project. Network size, the number of nodes, on the other hand, it's kind of boring in the sense that our models are not realistic anyways. We don't have billions of people, we don't have millions of nodes, we don't even have thousands. In most cases we have about 100 or less, which means that it's not representative anyways. So we probably don't want to play with this parameter. The only reason you would like to play with this parameter is to double check that your network makes sense, that your model makes sense at all. Because for very small number of nodes, it may not make sense, right? If you have only one node, obviously nothing will work because you'll have no connections. With two nodes, you'll have only one connection. You won't have cycles. With three nodes, you can have a cycle, but what you won't ever have. Well, you see the point, right? With three nodes, you cannot have a cycle and some degrees, some connections not existing, something like that. So while it's obvious for like 1, 2, 3 points, there is some chance that actually, even though a network of 10 points or of 20 points, as we have here in the picture, even though it looks fancy, maybe it's still not fancy enough to support certain type of effects. Think of modularity, for example, that I just described. In order to make nice modular network, you need to be able to break it into modules. So obviously, if your network is too small, it will be impossible to break it into interesting modules. So while a network of 10 or 20 may be large enough if you're just looking at this network, if you try to play with modularity, suddenly it may be too small, right? You will feel constrained. You won't be able to create 3 modules and then also regulate the density of connections in these modules. You just won't have enough space for that because the number of nodes is too small. So, but with a network of 100, you can probably have three modules and like varying degree of connectivity or whatever. And with a network of 1,000, it will be a piece of cake, right? So the network size matters, but only almost like a sense check. So it's one of those parameters that may be worth studying, but as a sense check. It won't be the figure 2 of your publication. If you're making a publication about that, so figure 1 is probably here's how we created a network and some sample data, and figure 2 is probably your main effect, your main question. So this probably won't be your main question. It will be like figure 4 or 5, which is, okay, now do you believe us? Let's double check that it's actually not a fluke, that it's not a weird property of this particular number of nodes, that it actually generalizes and applies to other numbers of nodes as well. So network size will just pick a decent number, but it's not a very deep interesting parameter for our purposes. Mathematically maybe, but not for practical purposes. Should I write something about that? Yeah, whatever. Let's keep it. Okay, let me write something. May not be the most interesting parameter to explore, except if as a sensitivity check. The number of edges. So the number of edges is important, but it is important in a peculiar way. The number of edges defines the network density, right? So it's not the total number of edges, but more like the average degree. So okay, so the number of edges equivalent to average degree defines the network density. And the situation with the number of edges is that for now we don't have control over it, because we just request this network, Barabasi network, and we have it. And the number of edges is kind of preset, because if we go here to the network creator, it creates the 0th node, it creates the first node and connects it to the 0th node. And then for every other node, it creates 2 edges, which means that if we have a network of n nodes, we will have like n minus 2, so all the younger nodes, multiplied by 2, because we add 2 edges for each of those nodes, plus 1, because 1 edge was created before that. So currently, currently, for our version of a Barabasi model is set at n minus 2 by 2. It's like, okay, let me just n minus 2 at 2 n minus 2 plus 1, which is not the smartest way to write that, but you get the point. So we don't have control over it. We could try to, but this would require rewriting the model, which is interesting, but it would take a little bit of an effort, because we would have to write, especially if we want to go with like if we want to make it smooth, if we don't want to have only one edge for every new node, 2 edges for every new node, 3 edges for every new node, if you want to have on average 2.5 edges for every new node, suddenly it can turn into a little bit of a tricky programming. I mean, it's not tricky, but it's like it's an undertaking which you can take. It should take a few hours, an hour or two, with all the troubleshooting. But yeah, that's something, but that's definitely not something that I'm going to do right now. So these are all about network creation. Now about the pandemic. Okay, let me finish the previous one, the number of edges, but we could conceivably make it more flexible. Actually, for the first one, let me add here. You know what? Yeah, I don't have to put numbers. So, but we can. For the first one, network type, we use the Barabasi model, but we can add a contrast with a different model, or we can mess with it. We can also use various rewiring procedures to gradually erode any given network configuration. May be useful for modularity studies if we ever do it. Yeah, I think we'll try to do something related in like this week, going to next week. But what else? So this was about network creation. But then we have the probability of disease propagation. Probability of disease propagation. The number of steps is not a parameter. I mean, it's an argument of a function, but ultimately it's just how deep we go. And obviously we want to, like in real life, we probably want to let it run either until it stops or, yeah, until it stops. So it's a practical thing, a practical argument that we pass to the function, but it's not a parameter of the model. Infectiousness period, though, is, so infectiousness period of infectiousness. And anything else? I think there is one more. Yeah, we now added vaccination rate, right? And actually, before we go there, so let me actually introduce two subtitles: network creation. That's for first three, and disease propagation. Except it won't now. I don't think it will. Yeah, it actually restarted. So we have vaccination rate. Another one that's here is the logic of disease propagation. For example, the number of states in like susceptible, infected, immune, right? The moment we change the logic for example, the number of states immune, the logic of becoming immune, etc. Like if we make, so for now, they stay infectious for the same amount of time, each of them, right? But we could make it probabilistic, or have a certain distribution of times, or which I don't want to do at all. It's a little bit too hard and of questionable. Like, it's not a very dramatic thing. I think the consequences won't be that dramatic. But if we, for example, include people who have recovered or acquired incomplete immunity, or if we add asymptomatic carriers or whatever, so any change of rules is obviously a hidden parameter of the model. Okay, so that's what we have. I think this model right now has about 7 things we can change about it, and some of those are deep, like the logic of disease propagation or the network type, and some of them are shallow, like the number of, like, probability of degree propagation. Yeah, it's just a number that's somewhere between 0 and 1. And so when we decide what to do with this model, we want to think about what do we want to change, because all the rest, all the parameters we want to set at some reasonable values, but we don't want to change them. We want them to stay the same, right? So if we're going to compare how the probability of disease propagation affects something, we want to set all other parameters at reasonable values and keep them stable. Yeah, and change only this one and see the consequences, right? And for this, for the purposes of this exercise, I will probably concentrate on 2, on the probability of disease propagation, number 5, and on period of infectiousness, number 6. And the vaccination rate, yeah, by the way, that's a wrong spelling, vaccination rate. So vaccination rate, I will leave it to you as an exercise, because it's a good exercise. But so, okay, we will be playing with it, we will be changing it, we will write a loop to change it for us automatically. Sure. What are the outcomes? So let's see. Let's look at our model and think, what are the outcomes? What can we measure? We actually already started measuring. So there are these 2 graphs that I haven't rerun since the last time. Are they still runnable? Nope. Because I removed the remove hub. Yeah, that's all right. But yeah, so this thing no longer works. But you remember it working. I shouldn't have done that. Uh-oh. Yeah, okay. Here it is. Uh-oh. Whatever. Here's the plot. So what was it? What was it? Yeah, right. So we have this way of tracking the results of, like, the statistics of our disease. We have this curve that shows new cases. It's already implemented, and it's actually a good curve. I mean, we implemented it because it's a good curve. So as I described in writing when I posted this assignment, our logic is that we always want to, so we should never start with what we can do and then try to, like, find the meaning in it. We should start with a question, so something we actually want to know, something that actually happens in the real world, and then try to find a way to translate it into our model. But in this case, we already kind of did this step when we implemented this curve, because we know that this curve is used in the real world, so we implemented it into a model. So this curve is also, in a way, a conceptual model of how we interpret the data, right? The results of our simulation. And as such, it is useful potentially. And so what in the real world, how this curve is useful? Well, one thing is this whole flatten the curve idea, right? The higher is this peak, the worse are the consequences for the society. The higher the peak, the more overloaded the medical system is, which means that the heights of the peak is one interesting parameter that we may want to track and report. So let's put it here. Heights, height of the new cases curve. Peak height of the new cases curve. The maximum stress on the medical system. That's kind of what it represents, right? What else? Well, as we make this curve slower, as the curve becomes slower, okay, just a second. This curve is really annoying because it actually uses infectious period now. So let me change that because I want a nice curve. Okay, so as the curve becomes kind of flatter, it also becomes longer. And so the length of the curve is another interesting thing, the shape of the curve, but the length of the curve is the most obvious measure of the shape that we can think of. It may be another parameter that we can measure, right? So let's write it here. See, that's a smoother curve. So we can look something like length of the curve. How do you measure the length of the curve? The peak is easy. You just find the maximum. That's the peak. So nothing to think about. What's the length of the curve, especially if it has this long tail at the end? Yeah, that's a little bit tricky, but we can do something like length at 20% of height. I mean, width at 20% of height. So at which point it falls below 20% of the peak, something like that, the length of the curve. So something like, actually, when does it reach the peak? When does it fall below the given percent, say 20% of the peak, stuff like that. And that's good, that's useful. It's harder to measure, and it's slightly, yeah, but that's also important, actually. Yeah, I was about to say it's slightly less important, but that's something that people are thinking a lot now about when the pandemic ends, right? How long will the lockdown continue? So that's another outcome that we can measure. It's a little bit tricky to measure, though, so maybe I'll pass on that. What else? Anything else? From the curve, we can probably, that's probably two most obvious parameters. You can try to assess the shape of the curve in some other ways. But another thing, if you look at these pictures that we have here, another interesting aspect is, what's the most obvious thing to measure? That's a rhetorical question for you. What do you think? It is, of course, the total number of cases, right? And it was not that much of an outcome before, because before we always have the network fully connected, so there were no lonely nodes, which means that every node was infected eventually. But now, with this new mechanism, with these nodes becoming immune, as you can see, not necessarily all nodes will become infected. So the total number of nodes infected suddenly is not always 100%. And if you think of it, yeah, so if we, okay, let me first try that. I'll actually put it first because it's the most obvious one. the total share of nodes infected, right? So you can imagine that if the disease, the propagation if the disease is highly contagious, if the probability of propagation is very high, and it takes really long to become immune, like what I did here, I set infectious period to 100, which is ridiculously long, considering that we only run it for 30 days. It's like never, essentially. So if the probability is high and it takes lots of time to become immune, everyone will get infected. On the other hand, if probability is low, but you get immune almost instantaneously, no one will get infected, right? So we can get all values here from almost 0% to almost 100%, from share of almost 0 to share of almost 1, which means that that's a good output. And so now, as I analyzed what I can even ask with this model and what I can even do with this model, I want to pick one, maybe two. So I will do two, but in your projects probably do one for your models. One thing that I will change, or two things that I will change. Well, actually first one, but then you can add the other if you want to. And yeah, so we want to limit, to narrow down, to narrow the scope of our question, because we cannot do everything. We should concentrate. We should do something that's actually doable and that's actually useful. So we should change one, maybe two parameter, and we should measure one at first, maybe two later, but with first one output, one parameter, one output. So let's look at that. Let's start with so that what I will be measuring will always be the total share of nodes infected, just because it's so obvious, so easy to measure. So just how will I measure that? That's another question that we should ask. Well, you just run a model and then I will look at the status of different nodes, right? So, and I will count those that are immune. By that time, there will be no infected nodes. All of them will be immune because it will be over. And I will count those that are immune, or count those that are still susceptible, which is like total number minus immune. So I know that. I know what I will be measuring. What will I be changing? Say probability of disease propagation for now, and then I'll add the period of infectiousness into the fray as well. All right, let's do that. And I will torture this little one. So it will become my computational experiment. Number of steps. Let's actually increase it to 100, because in some cases it may be pretty slow, the propagation of the disease. And trials, 500. Okay, this I want to change to 1 for now. And nodes. How many nodes do I want to have? Let's do something like, so I want some number that as small as possible, but not smaller. It's a saying, I feel. The model should be as simple. Everything, is it Albert Einstein? Everything should be made as simple as possible, but not simpler, which is the motto of modeling. So you want the model to be as simple as possible, but while it still replicates some complexity of the real world, but not simpler, because then the complexity will vanish, will disappear. So we want as few nodes as we can afford without making the network trivial. So let's go with, I don't know, 20, 30. Let's go with 20 at first. We won't even do 100. All right. And by the way, yeah, and trials 1. And by the way, number of nodes and number of trials have a little bit of antagonistic pull on it. So if you have few nodes, everything will be very rough, right? Which means that we will have to run more trials in order to get a smooth curve. If we have more nodes, the curves will look more smooth. It doesn't mean that they necessarily will be more smooth, because especially if you try to make your network modular, they may be smooth, but they may still differ from each other a lot. Imagine like if you have a community and it has Amish people and like, I don't know, Freemasons and someone else. So the disease will probably first, and so you have two sub-communities that don't interact that much, and so your typical curve would have like one hump for one sub-community and then another hump from another sub-community, but the position of these humps may change a lot depending on which node was infected first. Was it the node that was shared between the community, or one of the nodes that is deep inside the community? And also just on the particular instantiation of your network, because we'll be rebuilding networks at each run, right? So increasing the number of nodes will make curves look smoother, but won't necessarily make them truly smoother. They can still be variable. Increasing the number of trials, though, will definitely bring us towards the average behavior for the system. So I'm guessing for now, for this purpose, I will probably keep the number of nodes relatively low, like 20, but the number of trials I will later increase. Probability of propagation, sure, whatever. I'll actually change it. Should I even have it? I probably shouldn't. So this one counterintuitively is gone because it's no longer a fixed parameter. I will change it. Well, let me comment on that. No longer a constant. But what will be a constant for now is infect period. And I will make it equal to something like in between, like 10 for now. For now, later we'll see. Good. So I think that's all. That's all parameters that we have access to, right? Because density of the network is kind of hard-coded right now. The number of edges is linked to the network size, which is one of the limitations of what we have on hand. But yeah, as I told before, let's park it. So, okay, so history and steps and trials by 2. Oh, that's to compare stuff. So we're not comparing stuff for now. And steps and trials. For now, I want to have one curve. No? Yes? No? No? Yes? Sorry, that's bizarre. No, actually, yeah. I will be changing the probability, which means that probability of disease transmission will take several values. So I will run n trials for each of the values of probability, right? So I have actually specify one parameter, n probability steps. And I will set it to 2, which is the smallest number, that's not 1. So I want, what are the extremes? Probability of 0, no propagation. Should I model it? No, that's stupid, right? We know the value for 0. Only the initially infected node will be infected. No else will be infected. Probability of 1. Is it stupid? No, actually not. Because even with probability of 1, if the network is not fully connected, and ours is not, it will take a while for the disease to propagate. So what will happen is our probability will take that, like this many values, in equal steps from 1 over n to 1, inclusive. We're not modeling 0. So for 2 steps, we'll have 2 points. One will be a half, and the other will be 1. Right? For 3 steps, it will be a third, 2/3, 3/3. Yeah, so now we have it. And for each of those, let's actually move n trials lower. it's not changing the code, but it changes the, let's make it the last one. It changes the logic. So n trials, because this is n trials for each value, for each combination of parameters. All right. N trials equals 1. And this means that, what does it mean? What am I trying to say? Yeah, that when we, oh wait, do we even need history? Okay, so what I was about to say is that we need to multiply n trials by n probe steps to have the total number of traces we want to save. And that's true, we can do that. It's just that actually I wanted to measure something different, right? I wanted to measure the total sick, but that's okay. Let's have some pictures as well. So total infected, total infected, infected. Total infected equals how many different points will we have? How many different configurations? For now, just n probability steps, right? So total infected for each configuration, and this is the configuration, like this plus the probability that will be calculated dynamically gives us the configuration. So right now, the way it's coded, we'll have as many configurations as we have n probability steps, and for each configuration, we want to know the average number of cases that was there. So total infected equals np zeros. Shape equals just this number. Oh, oops. Right? Total infected. It's just a bunch of zeros. In this case, it will be 2 zeros, and then we will overwrite them. Yep. Right. So total infected. Okay. So for now, let's write a loop that goes around the number of trials, and now around the trials loop, the loop that will change the probability. So for I probe in range n probe steps, something, and then this thing. So let me rename this I into I trial, just because I don't want to be confused about what I it is. Okay. So something what? Probability equals, now I need to write a formula for probability. So the formula should be that when I probe is 0, it should be actually 1 over the number of steps. And when I probe is number of steps minus 1, which is the last value that it actually takes, it should be equal to 1. The probability should be equal to 1, right? Because probability of 0 is not worth checking. So the first one that we want to check is 1 over n probe steps. And then we want to do 2, 3, 4, and so on until 1. So how does it work? We need to do probability, I probe, I mean the number of the step, which starts from 0, and we want to change it to 1. And I think that's it, right? If we do this, because it will start with 1 over this value, and we'll add at this value divided by itself, which gives us a 1. So this will change the probability of disease propagation, which means that we should put it here in the formula. Right. And steps works here, and nodes should actually go here instead of 100. And steps infectious period is replaced with the constant for infectious period. And this way we'll have all the histories. And then for now, this plot doesn't make sense because it's the average of all, but it should almost work, except it doesn't, because I lost a letter. Yeah, it kind of works. That looks horrible. Why does it look so horrible? I mean, it should be fast. With disease probability, with the probability of propagation of 1, it should propagate through the network really fast. But is it really that fast? Okay, let me actually like change n steps to 10. Oh yeah, it's fine. It's fine. Look, it's not a 1 value. On average, we have like 6 new cases at step 1, 11 new cases at step 2, like whatever, 9 new cases on step 3. So there is actually a curve. Good. Let's now do the following. Let's now, and this is a tangent, by the way, because I totally didn't want to explore the curve, but I got, so this part can be eliminated because I promised you and myself that I will be looking at the total share of nodes infected. But somehow I want the curves as well. Is it a smart thing to do? Yes and no. Yes, because I'm on a tangent and I tried to, so I'm doing something that I didn't promise you to do, and like which is equivalent to getting distracted and changing the scope of your project in the process of running it. But at the same time, this curve is kind of helpful to me because it gives me some way of troubleshooting, of getting a feeling of whether the model even works. Like this troubleshooting, visual troubleshooting of actual state of the model is even better. But the curve is still reasonable, because right now what we're having is weird. We're averaging all of those, but we want to actually compare curves for different values of probability. I mean, that's not it. Different values of probability, right? So let's do that. We want to now plot all of these curves. So let's do that. We will do another loop for iProb in range and probe steps. So we'll go through this loop once again, just because I don't want to plot anything inside this loop. And then we will plot them, but the label will be like this thing. And we won't be averaging all of it. So we'll averaging all vertically all the time, true, but it won't be like from 0 to n trials. It will be, oh, it was to n trials actually. Anyways, sorry. Yeah, it wasn't the average of the entire thing. It was average of the first half. So now we want to do something like 0 to n trials, which is only n trials, but we want to do different n trials for different. Oh, can we do that? No, we cannot do that. Sorry. Oops. I got confused with MATLAB. So we want to start at 0 for the 0th probability, but we won't start at n trials for the second probability, and we won't start at 2 n trials for the third probability, and so on. Actually, no. Like I said everything in human terms, but in because Python is 0 indexed. So we should start from 0 for trial 0. We should start at n trials at trial 1. We should start at 2 n trials at trial 2, which means that we know the formula. It's just n trials multiplied by iProb. That's the first one. And the second one is basically the same thing plus n trials, which is n trials multiplied by iProb plus 1. Right? So this thing will average, we'll go through this, through everything that through the history, through everything we accumulated, and we'll average the first few columns, the second few columns, the third few columns, and so on. So let's try that. Nope. Or yep. Nope. Oh, look, this didn't work. Okay, I know why. I know why, because it didn't change this thing here. I'm still saving it and trial. Good. So we basically need, see, I was like wrong and then wrong in a different part, but it's all getting together. If we are going to save it, we should be doing it here at iTrial plus iProbe, same thing as before. I mean, same thing as here below. iProbe multiplied by n trials. This way, for the first trial of the 0th probability, this will be equal to 1. But for the first trial of, like first in Python terms, for the nth trial, for the trial I, 0th probability, this thingy will be equal to I, but for the next probability, it will be I plus n trial, then I plus 2n trial, and so on, right? So this should work. Yay, look at that. At when the disease was, when the probability of propagation was lower, it propagated slower, which is reasonable. So let's increase. Right now we have only n trial of 1. Okay, let's do n trial of 10. This is smoother. Yeah, a little bit. Let's do n trial of 100. Okay, look, we have almost a smooth curve. Good. Let's now, instead of 2 probability steps, let's go for 5 probability steps. That will take a while. Oh, look at that. We actually, for the smallest degree, for the smallest probability of 0.2, the pandemics didn't finish. So we want to model for more. Instead of n steps, we want to model for 30 steps or something. Okay. We have a family of curves for different probabilities of disease propagation. We have it slower or we have it faster. Okay, let's change it then steps back to 20. All right, that's good. That's good. So now we can go back to my original plan and look at the total number of people infected, of nodes infected. One thing though is that, so before we do that, another tangent, another little detour. The thing is, as you can see now, depending on the values that we put in here, sometimes the model is over very early, and sometimes it's running for longer. And when the model is over very early, right now, this loop in the disease propagation part keeps rotating. It keeps going through steps, except nothing is happening anymore. But it still goes through all the nodes, and for each node it checks whether it's infected, and it's no longer infected, but it does all this empty work. Which means that we would actually save time if we made it quit early. And I want to do that because I want to have a smooth curve, which means that I want to run quite a few trials, which means that I really want to like save a little bit of time. So basically, I want this thing to stop running if there are no active infection in the model. How to do that? So we should go through all the nodes, and then if it was in vain, we should do something. So let's code it like that. Let's set a flag, and the flag will be set, like flag is a Boolean variable, so we'll say, okay, it's done. Like nothing was found, and we will at first say yes, nothing was found, and then if something was found, if there was an infected node, so if we actually entered this part of the code, then we will switch the flag. It's not the best explanation, but let me do it the other way around. So, oh, actually, I don't even have to do that. I have a variable newly infected, so I can just check if newly infected is empty, by the time we reach this point, then nothing was found. So there are no infected points. So yeah, right? No. Don't listen to me. No, that's not true. That's not true because it's probabilistic. We can have an infected node sit there for quite some time, and then on the last day on its infectious period, infect new node. So no, we cannot do that. We can have it. We have to do a different flag. So flag still no flag is bad. Is still is active. And originally we set it to false, but then if we find at least one infected node, we will set it to true. So if g-values is infected, if the node is infectious, is active equals true, right? So if at least one infected node was found, it will be set as true. And we can compare it somehow, somewhere. Like, I mean, we can check it. If is active, so if not is active, which means that it's over, then we're done. So we could do just return and be done with it. The problem with doing return is that, like return history, is that history may be shorter than expected, right? Because if somebody, like some other part of the code, asked the model to run for 10 steps, and the model was done at step 2, so history is now only 2 columns wide, or no, it's not columns, it's elements, right? It's only length 2. And the code outside will expect length 10. So we want to pad this history with something. With what? With, of course, zeros. Oh, okay. This also didn't apply. We initialize history as zeros. Okay, everything is fine. We can actually return history. So if everything is dead, history still has all the zeros there for the rest of it, and we can just return it and be done with it. So the only thing that I want to check is whether we should return this time or next time. So if we enter the nodes and there are no active nodes, then obviously there was no newly infected nodes as well, which means that there is nothing to add to history. Yeah, so this works. This works, and this will make things faster. But let's run the test. Because, you know, here, for last 2 steps, there were no infected nodes, but there was no error, which means that it totally does tolerate, like, being asked to run when there are no infected nodes. So what happens is that it just does nothing, which is okay. All right, good. So now we supposedly made it faster. Yep, I think it's faster. It feels faster. We can time that. But it's faster because for most high probability propagation experiments, it doesn't run for a full 20 cases. Oh, actually, see, look at, no, what? No, yeah, so yeah, it doesn't run for full 20 cases, it stops earlier, which means here's a good test. So look, here's for 20 steps, here's the for 200. Same time, right? Which means that it actually did stop here at around 20. So this running it for 200 did not change anything, which means that we can now be a little bit more casual about the number of steps that we pick, because it now mostly affects the scale of this plot. It doesn't make it run longer. Yay, that's good. Okay, so what's missing? My original question is missing. My original question was the total number of nodes that got sick. How do we get that? We have to count them. Okay, so total infected, I created the variable total infected, and now I need to, after each trial, oh no, total infected. So total infected, it won't have n probability steps. It will be, so let's think. Ultimately, I want to have one average value for each value of n probability steps. So for each probability, I want to have one value, right? The average value of nodes that survive. So if I have 2 probability steps, or in this case I have 5 probability steps, I will want to have 5 points. However, in order to calculate the average, I should calculate those individual values and then sum them up and then divide by the number of trials, right? So I can do it without remembering them. I can just keep adding them to a sum, and at the end divide by the number of steps, right? So I can have a 0, then add the value from the first trial, add the value from the second trial, and at the very end divide by the number of trials. But maybe there is a point in remembering all the values from each trial. Why? Because it will actually give me an opportunity to also plot not just means, but also standard deviations, right? Because typically in a plot in science, we're not only interested by the mean, we're also interested by how variable the value is. So let's actually keep all of the data. So we will keep the result for every trial so that we can later calculate standard deviations as well. But then the question, how do we keep this data? Number of, so total infected and zeros. We can, of course, like put them all in one line. So the first few will be for one thing, the second few will be for another thing. It's kind of how we arrange the columns here. But I don't want to do that. Let's use, because in NumPy we can have all these dimensions. So let's use dimensions. Let's have it n trials by n probability steps. So this way, the first axis will be for different trials. So all these values will be like siblings. They will come from the same set of parameters, and they will be different just because the networks were different. The first network to get sick was different, and the dice that was tossed during the disease propagation was different, right? All the natural variability for this network configuration. But the next axis will be all the probability steps. Good. So, which means that total infected, like I trial and I probe, that's how we address one element here, and it will be equal to like count infected, something that we haven't calculated yet. We have to actually calculate it. So let's do that. Count infected equals 0. For, we need to go through all nodes. For node in how do we do that? I forgot. How do we go through nodes? For node in nodes, where nodes are get nodes. So if we do, sure, let's do that. No, we can do it better. We can make it easier. So because the only thing that we care about is G values, and there will only be interested in the status. So we can do this thing for key value, where key is actually a node. For node value in G values, items, right? That's the correct syntax to iterate through a dictionary. If value 0 equals whatever it is, which is okay, let me think. At the very end, so what do we want to count? We want to count, oh my god. I suddenly realized that we will run into a little issue when we do vaccinations. Okay, so if there is no vaccination, then we can just count all nodes that are immune, because the only way to get immune now is to get sick at some point. So if we do just that, if value 0 equals immune, then count infected is increased by 1. So this is enough. This will work, right? One footnote for the future: when you play with vaccination rates, we should somehow differentiate between nodes that got immune because they got sick and nodes that got immune because they were vaccinated. So one option is to just keep track of how many nodes are vaccinated, and somehow making the model report it outside of the model. Right now, the only thing that the model reports is the history, and it also changes the status of the network. But what's the other way of doing that? The other way of doing that is to vaccinate, when we vaccinate them, not make them immune, but make them vaccinated and consider it as a fourth state. So not post-disease, but like vaccinated, and change the logic above there. Yeah, both options would work, but okay, that's not relevant here. So for node value in G value items, if it's immune, count it, and then set this value to the total value. It should still work. No, it doesn't. Count infected because somebody didn't type properly. Okay, so it works, which means that total infected presumably is equal to something now. So total infected. Yep, all of them got infected, always? That feels wrong. Oh yeah, no, it's fine. Infectious period is 10. Yeah, it's very large. Okay, let's park it. So let's plot it instead of making a full picture. Instead of looking at all the numbers, let's plot it. How to plot it? Let's make a figure that's like wide, so like 12 by 5, and we keep the curves just because why would we get rid of the curves? There's a beautiful curves. And we do it plt subplot 1 to 1, but then we also add plt subplot 1 to 2, and here we will do plt so now we want the average number. Okay, let's okay, plt plot. What we want to do is plot I really want to have access to probabilities. So I want X to be actual my probabilities, but I have recalculated this twice already. I calculated it here, and I calculated it here, and now I want to calculate it a third time. That's not right. So let's make probabilities into an array. I want to calculate it once and just refer to it, otherwise we can get confused. So probabilities equals numpy zeros length of n probe steps. And here I will say that probability I probability equals this thing. And then every time the probability is mentioned, I will replace it with this array. And this is one time that it's mentioned. This is the other time that it's mentioned. And okay, let's check whether it works for now. Yeah, it works for now. And now we will use these probabilities as x values, and we'll use total infected as y values. Will it work right like that? Nope. Okay, x and y must be the same first dimension. They have shapes, so we have 5 probabilities. But the thing with the total infected is that the first dimension is actually trials. Okay, let's average then. Let's do average. And p average, and that's something that we've done a few weeks ago. Weeks ago. So we average across all trials, but we leave probabilities, right? So x's equals 0. Yep. Okay, let's suppress output. So for now, it's really annoying. No. See, that's the fun part. That's actually MATLAB syntax. Maybe probably some older syntax, older than MATLAB. If you put a dash and a point, it interprets it as a line with dashes and points. But if you do point and dash, then it interprets it as a line with markers. Okay, so we have a line with markers, and right now all 20 of those, all 20 nodes get infected. So first of all, total infected, we want it to be a ratio. So let's do this thing divided by the n nodes. Do you want percent? Like normal people like percent, scientists like shares. Okay, let's be scientists, all right? So, okay, good, that will be fine. Let's add labels. PLT X label is, what is that? Probability? Probability. Spread, disease, spread, probability of contagion. It's kind of daily probability of contagion. Daily probability of contagion. Yeah, maybe there is a better word for that, but I'm not an epidemiologist, so I don't know. PLT Y label is, you're welcome to check, you're welcome to see how normal people call that. So PLT Y label is share of population affected. All right, and you know what? Let's actually, because see, it's weird. It adds at 1. That's good. It starts at, right now, it starts at bizarre value. So let's do PLT. Let's do the limits. Always go from 0 to 1. PLT, I think it's Y lim, and I think you just provide 2 values, right? Yep. And for some reason, we have to always suppress the output. Okay. Yeah, and right now always the full share of population is sick. But let's try to reduce, let's make infectious period like not 10 days, but 2 days. Now drum roll. Oh yeah, it works. Look at that. So yeah, now it works. Let's go with 20 steps instead of 50 steps. So look, with this, with 2 days, with only 2 days that every person is infectious. If every person is infectious for only 2 days, infecting others actually becomes harder. So even with like 0.6 probability of propagation, disease propagation. We don't necessarily always infect all people. And 0.6 is huge, right? If you think of that. Daily. So yeah, so we have some sort of a curve. Yep. And if we lower the infectious period even more to 1 day, yeah, we have another curve. Right? So basically, let's set it to 2 days. Basically, this is some good analysis for one parameter, right? Because all parameters except one, except the daily probability of contagion, are fixed. And this is enough for a decent statement, a decent project. So even from this, you can say, well, when probability, when nodes stay infectious for only a limited amount of time, if the probability of disease propagation is small enough, the disease doesn't necessarily spread to all the nodes. Something that we had seen before. So this can be one figure in the paper, because that's the illustration of what's going on. But then as the actual result, you present this plot, and you can make it funnier, right? Let's make it fun. So let's go with 10 steps. It will make it smoother. Yay, look at that, it's smoother. How's about we add error bars? I actually don't know how to add error bars, but we can check. Oh, yeah, I remembered. I shouldn't create new windows, I should create new tabs. Okay, NumPy what? NumPy, no, not NumPy. Matplotlib error bars. Different ways of specifying error bars, visualizing errors. Okay, PLT error bar, X, Y, Y error. Yeah, that's good. That's good. I like that. Let's do that. Oh, and look, you don't have to actually do plot. So this comes on top of plot. This comes instead of plot. So this thing plots both Y as the center and also the error bar. That's sweet. Let's go and do that. So instead of this thing, we can mark that. We can still add a plot to connect them. So let's actually do this first. PLT error bar, X, Y, X is probability. Y is this thing. And Y error is almost this thing, except instead of NP average, we do an NP STD, right? Standard deviation. And we still divide it by the number of nodes, because standard deviation is, because the square root has the same scale as the values themselves, so you can, the scaling stays the same. FMT, I bet it's format. Okay, let's keep it. Bam. Almost good. And by the way, I'm doing it a little weirdly. I shouldn't probably do that. Let's make it. Oops. So let's create a new, because I don't have to rerun the entire model just to mess with the figures. I can just copy this thing lower and mess with it. So let's add a line now on top of. You know what? I probably want the line before. I want the line before. I want the line to be blue. I want this thing to be blue as well, because why not? This is disgusting. This blue is... No, I don't like this blue. I have a déjà vu. I think I said that before. Color, is it market? How to change the color? Oh, Lord. Okay. Matplotlib marker color. Is it some sort of face that, and this and that, and this and that? Marker face color. Okay, marker face color. marker face color equals blue. Oh, this is a good blue. This is a good blue. Unlike the other blue that was not good. Two commas. What? 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 Why are they yellow? Why are they orange? My goodness. Okay, so for error bars, they probably, because they have e-color. Good. Sure, we can do that. E-color. Where is my code? E-color equals blue. Marker face color equals blue. This is killing me. Look, plot is blue, but it's different blue than the error color blue. Error color is an incorrect blue, and by incorrect I mean that I don't like it. And marker color is incorrect blue as well. What the heck? Okay, let's torture it. So colors actually come from a special list of colors. Matplotlib colors. Apparently, it's like a giant list of colors that include lots and lots of literal values. I mean, we can set RGB values, but I want to use one of those colors. Where are they? There is a list of special color names, I think. Okay, colors is a module. We don't want a module. List of named colors. Oh, that's good. List of named colors. Look at that. This is a list of named colors. So we are getting something like dark blue. I want something like cornflower blue, royal blue. I like royal blue. Do I? Yes. No. I like Dodger blue even more. Dodger blue. So marker face color. Oh, I know why. That's because, silly me. No, this is logical. There are no markers in this line. There is only a line. So it should be like line color. No, line color doesn't exist. It should be like maybe just simply color. What's that? Plot. Color. Color is the color of the line. Okay, good. So like color equals blue. Yes. Except I hate blue, as it turns out. I like Dodger blue. Yes, Dodger blue is good. Replace, replace, replace. Yay, yay, that's nice. Okay, good, 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 good. Actually, let's make it black. Yeah, it's all right. Why aren't my error bars? Why don't my error bars have error bars? Why are they like that? I want them to be like that. I want them to have little dashes at the end. This is how to make it happen. It's cap size. Yeah, I think I've done that before. Cap size. So where does it go? Right, somewhere around here. And like cap size equals 1 equals 2 equals 5. Yay, that's good. Okay, so we have a plot with error bars. And we can actually see that the error bars are quite wide. So there is quite some variability. Right? So now I'm a little bit in a tough situation because I wanted to, but I guess I'm out of steam. So again, I won't actually do what I promised you to do. Because I promised you, I thought that I would explore an interplay between the probability of disease propagation. let me delete all the plots from here. So this is just run, and this makes all the plots. So I told you that I promised at some point that to show the interplay between the probability of disease propagation and infectious period, the period of infectiousness, because as you've noticed, if we make an infectious period long, then everybody gets sick. So this thing is always situated at 1. If, however, we make nodes recover really fast and become immune, then the disease has a hard time propagating. So even with relatively high probabilities, it doesn't necessarily infect all the nodes, right? So, which means that really it's not, this parameter is kind of special because it's not necessarily special, but this parameter is tightly linked to this other parameter. They are tightly linked. If you increase probability but also make nodes recover faster, sometimes you can have the same overall effect. Even the shape of the curve can potentially be the same, or not the same but similar, right? So one parameter can partially compensate for each other, which means that our choice of a value of the baseline value that we made 2 here matters a lot. So the number of nodes, for example, probably doesn't matter that much. If we do 30 nodes, let's do 30 nodes instead of 20 nodes. Yay, see, it's kind of, yeah, everything takes a little bit longer because the network is larger now. But the difference is not that drastic. If we go to, let's do, instead of 30 nodes, let's do 100 nodes. It will take a little bit longer now to calculate it, but let's see what we get. Yeah, the curves became a little bit longer yet, still. The probability went a little bit down because I guess there are nooks and crannies now in this network, and it's easier to have a few nodes that actually disease has a hard time propagating in a larger network if the density stays the same, because it's more elaborate, and so there are more parts of the network that can be isolated by immune nodes from the rest of the network. That's my interpretation. Maybe it's wrong, but that's my intuition, so kind of. But still, these changes are very subtle. So we just went from 20 nodes to 100 nodes, which is 5 times more, and it barely changed, right? However, if we go from 2 days to 3 days, the change will be ginormous. And let me remind you. So actually, let me copy this thing. Let me copy this thing again down. So this will preserve the old plot. And let me recalculate this plot. So this is the old node for 2 days. Here we will see the node for 3 days, except it's with 100 nodes now, so it takes a little bit to calculate. Yeah, look at that. So if you try to visually compare this plot to this plot, you can see that it's much higher, right? So with 2 days that every infected node remained infectious, at 0.4 probability we had 80% of network affected. Now with 0.4 we have like 90 something, 95% of network affected. So the effect is much stronger. The peak changed. Did the peak change? The peak actually didn't change much. Why didn't the peak change? Yeah, these are different plots, but for some reason these guys didn't change that much. Oh yeah, because the peakest peak corresponds to disease propagation of 1, which means that like everything is futile. Resistance is futile, everybody gets infected. It is the flattest curves that actually change. So here's the flattest curve, the orange curve sits inside the anyways, yeah, there are subtle changes, but this thing didn't change that strongly. Anyways, the effect of change in only one here, like if we switch to 5, so it was, remember, it was 5, it was 2. Let's make this thing 5 times larger. If nodes stay infectious 5 times longer, it's now much harder to stay alive. Actually, a big network is not that bad, unlike in a 20 nodes network, but still look. So now the numbers are much higher. So here almost nobody got infected, here 20% got infected. The length that the disease is there is much longer. So there are the changes. So what is the way, how can we, if the model is suddenly sensitive to one of our assumptions, how can we deal with that? One way to deal with that is to free this parameter as well, and also to analyze it fully. So what we did here is called a sweep, which is we swept through all values of this particular not all, but through values that, like, we swept through the entire range of values for this particular parameter for the probability, from basically 0 to basically 1 to actually 1, with a certain step. But all the rest are fixed. So we can do a double sweep. We can try all values of probability and all values of the number of days that the node stays infected, but within a certain range. And then instead of one plot here, we'll have a bunch of plots. And this plot with curves will become impossible to read. So you would have to only use some of these curves if you want to keep the curves. And for this plot, for the daily probability of contagion, we'll probably have to let go of error bars. And we may have to go for some sort of three-dimensional plot. And that was my intention originally, not to do a three-dimensional plot. I wanted to do a heat map. But you know what? I overestimated my, like how much time it would take as usual. So yeah, so let's not do that. And I'm leaving you with this. And what's your homework? So the second part of the homework is to replicate what is happening here. Let me actually delete this part, the lower part. So, but your goal is to replicate this code, to replicate the changes that we've made, to replicate this experiment. And then, ideally, try to, so that's the minimal set, replicate all that. The maximal set, try to do a similar analysis for a different aspect of the model. For example, maybe you know what, the easiest thing to do would be to do the reverse of that in a way. So here we set, in my model here that we see here, we set the infectious period and change the probability. So do is the other way around. Set the probability fixed at a certain reasonable value, and actually this analysis shows you which values are reasonable. For example, is value of 0.9 reasonable? Probably not, in the sense that it doesn't give you any interesting behavior. So set it in the, like, slightly lower, and change the infectiousness period and see what will be the shape of the curve if you keep the probability fixed and the period of infectiousness changes. All right. I think it's a good task. Okay then. Good. So good luck. Keep me posted if you have any questions, and till later.